On the 14th of August, 1894, an excited crowd gathered outside Oxford's Natural History Museum. This huge Gothic building was hosting the annual meeting of the British Association for the Advancement of Science. Over 2,000 tickets had been sold in advance, and the museum was already packed, waiting for the next talk to be given by Professor Oliver Lodge. His name might not be familiar to us now, but his discoveries should have made him as famous as some of the other great electrical pioneers of history. People like Benjamin Franklin, Alessandro Volta, or even the great Michael Faraday. Quite unwittingly, he would set in motion a series of events that would revolutionize the Victorian world of brass and telegraph wire. This lecture would mark the birth of the modern electrical world, a world dominated by silicon and mass wireless communication. In this program, we discover how electricity connected the world together through broadcasting and computer networks, and how we finally learnt to unravel and exploit electricity at an atomic level. After centuries of man's experiments with electricity, a new age of real understanding was now dawning. These tubes are not plugged in to any power source, but they still light up. It's electricity's invisible effect, an effect not just confined to the wires it flows through. In the middle of the 19th century, a great theory was proposed to explain how this could be. The theory says that surrounding any electric charge, and there's a lot of electricity flowing above my head, is a force field. These fluorescent tubes are lit purely because they're under the influence of the force field from the power cables above. The theory that a flow of electricity could in some way create an invisible force field was originally proposed by Michael Faraday, but it would take a brilliant young Scotsman called James Clerk Maxwell who would prove Faraday correct, and not through experimentation, but through mathematics. This was all a far cry from the typical 19th century way of understanding how the world works, which was essentially to see it as a physical machine. Before Maxwell, scientists had often built strange machines or devised wondrous experiments to create and measure electricity. But Maxwell was different. He was interested in the numbers, and his new theory not only revealed electricity's invisible force field, but how it could be manipulated. It would prove to be one of the most important scientific discoveries of all time.
Maxwell was a mathematician, and a great one, and he saw electricity and magnetism in an entirely new way. He expressed it all in terms of very compact mathematical equations. And the most important thing is that in Maxwell's equations is an understanding of electricity and magnetism as something linked and as something that can occur in waves.
Maxwell's calculations showed how these fields could be disturbed, rather like touching the surface of water with your finger. Changing the direction of the electric current would create a ripple or wave through these electric and magnetic fields. And constantly changing the direction of the flow of the current forwards and backwards like an alternating current, would produce a whole series of waves. Waves that would carry energy. Maxwell's maths was telling him that changing electric currents would be constantly sending out great waves of energy into their surroundings, waves that would carry on forever unless something absorbed them. Maxwell's maths was so advanced and complicated that only a handful of people understood it at the time. And although his work was still only a theory, it inspired a young German physicist called Heinrich Hertz. Hertz decided to dedicate himself to designing an experiment to prove that Maxwell's waves really existed. And here it is. This is Hertz's original apparatus, and its beauty is in its sheer simplicity. He generates an alternating current that runs along these metal rods with a spark that jumps across the gap between these two spheres. Now, if Maxwell was right, then this alternating current should generate an invisible electromagnetic wave that spreads out into the surroundings. If you place a wire in the path of that wave, then at the wire there should be a changing electromagnetic field which should induce an electric current in the wire. So what Hertz did was build this ring of wire, his receiver, that he could carry around in different positions in the room to see if he could detect the presence of the wave. And the way he did that was leave a very tiny gap in the wire across which a spark would jump if a current runs through the ring. Now, because the current is so weak, that spark is very, very faint. And Hertz spent pretty much most of 1887 in a darkened room staring intensely through a lens to see if he could detect the presence of this faint spark. But Hertz wasn't alone in trying to create Maxwell's waves. Back in England, a young physics professor called Oliver Lodge had been fascinated by the topic for years, but hadn't had the time to design any experiments to try to discover them. Then, one day in early 1888, while setting up an experiment on lightning protection, he noticed something unusual. Lodge noticed that when he set up his equipment and sent an alternating current around the wires, he could see glowing patches between the wires. And with a bit of tweaking, he saw these glowing patches formed a pattern. The blue glow and electrical sparks occurred in distinct patches evenly spaced along the wires. He realized they were the peaks and troughs of a wave, an invisible electromagnetic wave. Lodge had proved that Maxwell was right. Finally, by accident, Lodge had created Maxwell's electromagnetic waves around the wires. The big question had been answered. Filled with excitement at his discovery, Lodge prepared to announce it to the world at that summer's annual scientific meeting run by the British Association. Before it, though, he decided to go on holiday. His timing couldn't have been worse, because back in Germany, and at exactly the same time, Heinrich Hertz was also testing Maxwell's theories. Eventually, Hertz found what he was looking for, a minute spark. And as he carried his receiver around to different positions in the room, he was able to map out the shape of the waves being produced by his apparatus. And he checked each of Maxwell's calculations carefully and tested them experimentally. It was a tour de force of experimental science. Back in Britain, as the crowds gathered for the British Association meeting, Oliver Lodge returned from holiday, relaxed and full of anticipation. This, Lodge thought, would be his moment of triumph, when he could announce his discovery of Maxwell's waves. His great friend, the mathematician Fitzgerald, was due to give the opening address in the meeting. But in it, he proclaimed that Heinrich Hertz had just published astounding results. He had detected Maxwell's waves traveling through space. "We have snatched the thunderbolt from Jove himself and enslaved the all-pervading ether," he announced. Well, I can only imagine how Lodge must have felt having his thunder stolen. Professor Oliver Lodge had lost his moment of triumph, pipped at the post by Heinrich Hertz.
Hertz's spectacular demonstration of electromagnetic waves, what we now call radio waves, even though he didn't know it at the time, is going to lead to a whole revolution in communications over the next century.
Maxwell's theory had shown how electric charges could create a force field around them, and that waves could spread through these fields like ripples on a pond. And Hertz had built a device that could actually create and detect the waves as they passed through the air. But almost immediately, there would be another revelation in our understanding of electricity. A revelation that would once again involve Professor Oliver Lodge, and once again, his thunder would be stolen. The story starts in Oxford in the summer of 1894. Hertz had died suddenly earlier that year, and so Lodge prepared a memorial lecture with a demonstration that would bring the idea of waves to a wider audience. Lodge had worked on his lecture. He'd researched better ways of detecting the waves, and he'd borrowed new apparatus from friends. He'd made some significant advances in the technology designed to detect the waves. This bit of apparatus generates an alternating current and a spark across this gap. The alternating current sends out an electromagnetic wave, just as Maxwell predicted, that is picked up by the receiver. It sets off a very weak electric current through these two antennae. Now, this is what Hertz had done. Lodge's improvement on this was to set up this tube full of iron filings. The weak electric current passes through the filings, forcing them to clump together. And when they do, they close a second electric circuit and set off the bell. So if I push the button on this end, it sets off the bell at the receiver. And it's doing that with no connections between the two. It's like magic.
You've got to imagine a packed house, lots of people in the audience, and what they suddenly see is, as if by magic, a bell ringing. It's quite incredible.
It might not have been the most dramatic demonstration the audience had ever seen, but it certainly still created a sensation among the crowd. Lodge's apparatus, laid out like this, no longer looked like a scientific experiment. In fact, it looked remarkably like those telegraph machines that had revolutionized communication, but without those long cables stretching between the sending and receiving stations. To the more worldly and savvy members of the audience, this was clearly more than showing the maestro Maxwell was right. This was a revolutionary new form of communication. Lodge published his lecture notes on how electromagnetic waves could be sent and received using his new improvements. all around the world, inventors, amateur enthusiasts and scientists read Lodge's reports with excitement and began experimenting with Hertzian waves. Two utterly different characters were to be inspired by it. Both would bring improvements to the wireless telegraph, and both will be remembered for their contribution to science far more than Oliver Lodge. The first was Guglielmo Marconi.
Marconi was a very intelligent, astute and a very charming individual. He definitely had the Italian-Irish charm. He could apply this to almost anyone, from sort of young ladies to world-renowned scientists.
Marconi was no scientist, but he read all he could of other people's work in order to put together his own wireless telegraph system.
And it's possible that because he was brought up in Bologna and it was fairly close to the Italian coast, that he saw the potential of wireless communications in relation to maritime usage fairly early on. Then,
aged only 22, he came to London with his Irish mother to market it. The other person inspired by Lodge's lecture was a teacher at the Presidency College in Calcutta called Jagadish Chandra Bose. Despite degrees from London and Cambridge, the appointment of an Indian as a scientist in Calcutta had been a battle against racial prejudice. Indians, it was said, didn't have the requisite temperament for exact science. Well, Bose was determined to prove this wrong, and here in the archives we can see just how fast he set to work. This is a report of the 66th meeting of the British Association in Liverpool, September 1896. And here is Bose, the first Indian ever to present at the association meeting, talking about his work and demonstrating his apparatus. He'd built and improved on the detector that Lodge described, because in the hot, sticky Indian climate, he'd found that the metal filings inside the tube that Lodge used to detect the waves became rusty and stuck together. So Bose had to build a more practical detector using a coiled wire instead. His work was described as a sensation. The detector was extremely reliable and could work on board ships, so had great potential for the vast British naval fleet.
Britain was the centre of a vast telecommunications network which stretched almost around the world, which was used to support an equally vast maritime network of merchant and naval vessels which were used to support the British Empire.
But Bose, a pure scientist, wasn't interested in the commercial potential of wireless signals, unlike Marconi.
This was a sort of a new cutting-edge field, but Marconi wasn't a trained scientist, so he did come at things in a fairly different way, which may have been why he progressed so quickly in the first place. And he was very good at forming connections with the people that he needed to form connections with to enable his work to be done.
Marconi used his connections to go straight to the only place that had the resources to help him. The British Post Office was a hugely powerful institution. When Marconi first arrived in London in 1896, these buildings were newly completed and already heaving with business from the Empire's postal and telegraphy services. Marconi had brought his telegraph system with him from Italy, claiming it could send wireless signals over unheard-of distances. And the Post Office engineer-in-chief, William Preece, immediately saw the technology's potential. So Preece offered Marconi the great financial and engineering resources of the Post Office, and they started work up on the roof. The old headquarters of the Post Office were right there, and between this roof and that one, Marconi and the Post Office engineers would practice sending and receiving electromagnetic waves. The engineers helped him improve his apparatus, and then Preece and Marconi together demonstrated it to influential people in government and the Navy. What Preece didn't realise was that even as he was proudly announcing Marconi's successful partnership with the Post Office, Marconi was making plans behind the scenes. He'd applied for a British patent on the whole field of wireless telegraphy and was planning on setting up his own company. When the patent was granted, all hell broke loose in the scientific community. That patent was itself revolutionary. You see, patents could only be taken out on things that weren't public knowledge. But Marconi famously had hidden his equipment in a secret box. And here it is. When his patent was finally granted, Marconi ceremoniously opened the box. Everyone was keen to see what inventions lay within. Batteries forming a circuit, iron filings in the tube to complete the circuit to ring the bell on top. Nothing they hadn't seen before. And yet Marconi had patented the lot.
The reason why Marconi is famous is not because of that invention. He doesn't invent radio, right? But he improves it and turns it into a system. Lodge doesn't do that. And that's why we remember Marconi, and that's why we don't remember Lodge.
The scientific world was up in arms. Here was this young man who knew very little about the science behind his equipment, about to make his fortune from their work. Even his great supporter, Preece, was disappointed and hurt when he found out that Marconi was about to go it alone and set up his own company. Lodge and other scientists began a frenzy of patenting every tiny detail and improvement they made to their equipment. This new atmosphere shocked Bose when he returned to Britain. Bose wrote home to India in disgust at what he found in England. Money, 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 all the time. What a devouring greed. I wish you could see the craze for money of the people here. His disillusionment with the changes he saw in the country he revered for its scientific integrity and excellence is palpable. Eventually, though, it was his friends who convinced Bose to take out his one and only patent on his discovery of a new kind of detector for waves. It was this discovery that would lead to perhaps an even greater revolution for the world. He had discovered the power of crystals.
This replaces older techniques using iron filings, which are messy and difficult and don't work well. And here's a whole new way of detecting radio waves, and it's one that's going to be at the centre of a radio industry.
Bose's discovery was simple, but it would truly shape the modern world. When some crystals are touched with metal to test their electrical conductivity, they can show rather odd and varied behaviour. Take this crystal, for example. If I can touch it in exactly the right spot with the tip of this metal wire and then hook it up to a battery, it gives quite a significant current. But if I switch around my connections to the battery and try and pass the current through in the opposite direction, it's a lot less. It's not a full conductor of electricity. It's a semiconductor, and it found its first use in detecting electromagnetic waves. When Bose used a crystal like this in his circuits instead of the tube of filings, he found it was a much more efficient and effective detector of electromagnetic waves. It was this strange property of the junction between the wire, known as the cat's whisker, and the crystal, which allowed current to pass much more easily in one direction than the other, that meant it could be used to extract a signal from electromagnetic waves. At the time, no one had any idea why certain crystals acted in this way. But to scientists and engineers, the strange behavior had a profound and almost miraculous practical effect. With crystals as detectors, now it was possible to broadcast and detect the actual sound of a human voice or music. In his Oxford lecture in 1894, Oliver Lodge had opened a Pandora's box. As an academic, he'd failed to foresee that the scientific discoveries he'd been such a part of had such commercial potential. The one patent he had managed to secure, the crucial means of tuning a receiver to a particular radio signal, was bought off him by Marconi's powerful company. Perhaps the worst indignation for Lodge, though, would come in 1909, when Marconi was awarded the Nobel Prize in Physics for wireless communication. It's difficult to imagine a bigger snub to the physicist who'd so narrowly missed out to Hertz in the discovery of radio waves, and who'd then go on to show the world how they could be sent and received. But despite this snub, Lodge remained magnanimous, using the new broadcasting technology that resulted from his work to give credit to others, as this rare film of him shows.
Hertz made a great advance. He discovered how to produce and detect waves in space, thus bringing the ether into practical use, harnessing it for the transmission of intelligence in a way which has subsequently been elaborated by a number of people.
Today, we can hardly imagine a world without broadcasting. To imagine a time when radio waves hadn't even been dreamt of. Engineers continued to refine and perfect our ability to transmit and receive electromagnetic waves. But their initial discovery was ultimately a triumph of pure science, from Maxwell through Hertz to Lodge. But still, the very nature of electricity itself remained unexplained. What created those electrical charges and currents in the first place? Although scientists were learning to exploit electricity, they still didn't know what it actually was. But this question was being answered, with experiments looking into how electricity flowed through different materials. Back in the 1850s, one of Germany's great experimentalists and a talented glassblower, Heinrich Geissler, created these beautiful showpieces. Geissler pumped most of the air out of these intricate glass tubes and then had small amounts of other gases pumped in. He then passed an electrical current through them. They glowed with stunning colours, and the current flowing through the gas seemed tangible. Although they were designed purely for entertainment, over the next 50 years, scientists saw Geissler's tubes as a chance to study how electricity flowed. Efforts were made to pump more and more air out of the tubes. Could the electric current pass through nothingness, through the vacuum? This is a very rare flickbook film of the British scientist who created a vacuum good enough to answer that question. His name was William Crookes. Crookes created tubes like this. He pumped out as much of the air as he could so that it was as close to a vacuum as he could make it. Then, when he passed an electric current through the tube, He noticed a bright glow on the far end. A beam seemed to be shining through the tube and hitting the glass at the other end. It seemed at last we could see electricity. The beam became known as a cathode ray, and this tube was the forerunner of the cathode ray tube that was used in television sets for decades. Physicist J.J. Thomson discovered that these beams were made up of tiny negatively charged particles, and because they were carriers of electricity, they became known as electrons. Because the electrons only moved in one direction from the heated metal plate through the positively charged plate at the other end, they behaved in exactly the same way as Bose's semiconductor crystals. But whereas Bose's crystals were naturally temperamental, you had to find the right spot for them to work, these tubes could be manufactured consistently. They became known as valves, and they soon replaced crystals in radio sets everywhere. These discoveries would lead to an explosion of new technology.
Early 20th century electronics is all about what you can do with valves. So the radio industry is built on valves. Early television is built on valves. Early computers are built with valves. These are the things that you build the electronic world with.
Having discovered how to manipulate electrons flowing through a vacuum, scientists were now keen to understand how they could flow through other materials. But that meant understanding the things that made up materials, atoms. It was in the early years of the 20th century that we finally got a handle on exactly what atoms were made up of and how they behaved. And so what electricity actually was on the atomic scale. At the University of Manchester, Ernest Rutherford's team was studying the inner structure of the atom and producing a picture to describe what an atom looked like. This revelation would finally help explain some of the more puzzling features of electricity. By 1913, the picture of the atom was one in which you had a positively charged nucleus in the middle, surrounded by negatively charged orbiting electrons in patterns called shells. Each of these shells corresponded to an electron with a particular energy. Now, given an energy boost, an electron could jump from an inner shell to an outer one, and the energy had to be just right. If it wasn't enough, the electron wouldn't make the transition. And this boost was often temporary because the electron would then drop back down again to its original shell. As it did this, it had to give off its excess energy by spitting out a photon. And the energy of each photon depended on its wavelength, or as we would perceive it, its color. Understanding the structure of atoms could now also explain nature's great electrical light shows. Just like Geisler's tubes, the type of gas the electricity passes through defines its color. Lightning has a blue tinge because of the nitrogen in our atmosphere. Higher in the atmosphere, the gases are different, and so is the color of the photons they produce, creating the spectacular auroras. Understanding atoms, how they fit together in materials, and how their electrons behave was the final key to understanding the fundamental nature of electricity. This is a Wimshurst machine, and it's used to generate electric charge. Electrons are rubbed off these discs and start a flow of electricity through the metal arms of the machine. Now, metals conduct electricity because the electrons are very weakly bound inside their atoms and so can slosh about and be used to flow as electricity. Insulators, on the other hand, don't conduct electricity because the electrons are very tightly bound inside the atoms and are not free to move about. The flow of electrons, and hence electricity, through materials was now understood. Conductors and insulators could be explained. What was more difficult to understand was the strange properties of semiconductors. Our modern electronic world is built upon semiconductors and would grind to a halt without them. Jagadish Chandra Bose may have stumbled upon their properties back in the 1890s, but no one could have foreseen just how important they were to become. But with the outbreak of the Second World War, things were about to change. Here in Oxford, this newly built physics laboratory was immediately handed over to the war research effort. The researchers here were tasked with improving the British radar system. Radar was a technology that used electromagnetic waves to detect enemy bombers. And as its accuracy improved, it became clear that valves just weren't up to the job. So the team had to turn to old technology. Instead of valves, they used semiconductor crystals. Now, they didn't use the same sort of crystals that Bose had developed. Instead, they used silicon. This device is the silicon crystal receiver, as a tiny tungsten wire coiled down and touching the surface of a little silicon crystal. It's incredible how important a device it was. It was the first time silicon had really been exploited as a semiconductor. But for it to work, it needed to be very pure. And both sides in the war put a lot of resources into purifying it.
In fact, the British had better silicon devices. So they must have had some growth of silicon already at that time, which we were just started with, in Berlin.
The British had better silicon semiconductors because they had help from laboratories in the US, in particular the famous Bell Labs. And it wasn't long before physicists realized that if semiconductors could replace valves in radar, perhaps they could replace valves in other devices too, like amplifiers. The simple vacuum tube with its one-way stream of electrons had been modified to produce a new device. By placing a metal grill in the path of the electrons and applying a tiny voltage to it, a dramatic change in the strength of the beam could be produced. These valves worked as amplifiers, turning a very weak electrical signal into a much stronger one.
An amplifier is something, in one sense, really simple. You just take a small current, you turn it into a larger current. But in other ways, it changes the world, because when you can amplify a signal, you can send it anywhere in the world.
As soon as the war was over, German expert Herbert Maturay and his colleague Heinrich Welcker started to build a semiconductor device that could be used as an electrical amplifier. And here is that first working model that Maturay and Welcker made. If you look inside, you can see the tiny crystal and the wires that make contact with it. If you pass a small current through one of the wires, this allows a much larger current to flow through the other one. So it was acting as a signal amplifier. These tiny devices could replace big, expensive valves in long-distance telephone networks, radios, and other equipment where a faint signal needed boosting. Maturay immediately realized what he'd created, but his bosses were initially not interested. Not, that is, until a paper appeared in a journal announcing a Bell Labs discovery. A research team there had stumbled across the same effect, and now they were announcing their invention to the world. They called it the transistor.
They had it in December 1947, and we had it in beginning 48, but just life, you know. They had it a little bit earlier, the effect. But funny enough, their transistors were just no good.
Although the European device was more reliable than Bell Labs' more experimental model, neither quite fulfilled their promise. They worked, but were just too delicate. So the search was on for a more robust way to amplify electrical signals. And the breakthrough came by accident. In Bell Labs, silicon crystal expert Russell Ohl noticed that one of his silicon ingots had a really bizarre property. It seemed to be able to generate its own voltage. And when he tried to measure this by hooking it up to an oscilloscope, he noticed that the voltage changed all the time. The amount of voltage it generated seemed to depend on how much light there was in the room. So by casting a shadow over the crystal, he saw the voltage dropped. More light meant the voltage went up. What's more, when he turned a fan on between the lamp and the crystal, the voltage started to oscillate with the same frequency that the blades of the fan were casting shadows over the crystal. One of Ohl's colleagues immediately realized that the ingot had a crack in it that formed a natural junction. And this tiny natural junction in an otherwise solid block was acting just like the much more delicate junction between the end of a wire and a crystal that Bose had discovered. Except here it was sensitive to light. The ingot had cracked because either side contained slightly different amounts of impurities. One side had slightly more of the element phosphorus, while the other had slightly more of a different impurity, boron. And electrons seemed to be able to move across from the phosphorus side to the boron side, but not vice versa. Photons of light shining down onto the crystal were knocking electrons out of the atoms, but it was the impurity atoms that were driving this flow. Phosphorus has an electron that is going spare, and boron is keen to accept another. So electrons tended to flow from the phosphorus side to the boron side, and crucially only flowed one way across the junction. The head of the semiconductor team, William Shockley, saw the potential of this one-way junction within a crystal. But how would it be possible to create a crystal with two junctions in it that could be used as an amplifier? Another researcher at Bell Labs called Gordon Teal had been working on a technique that would allow just that. He'd discovered a special way to grow single crystals of the semiconductor germanium. In this research institute, they grow semiconductor crystals in the same way that Teal did back in Bell Labs. Only here, they grow them much, much bigger. At the bottom of this vat is a container with glowing hot molten germanium, just as pure as you can get it. Inside it are a few atoms of whatever impurity is required to alter its conductive properties. Now, the rotating arm above has a seed crystal at the bottom that has been dipped into the liquid and will be slowly raised up again. As the germanium cools and hardens, it forms a long crystal like an icicle below the seed. The whole length is one single beautiful germanium crystal. Thiel worked out that as the crystal is growing, other impurities can be added to the vat and mixed in. This gives us a single crystal with thin layers of different impurities, creating junctions within the crystal. This crystal with two junctions in it was Shockley's dream. Applying a small current through the very thin middle section allows a much larger current to flow through the whole triple sandwich. From a single crystal like this, hundreds of tiny solid blocks could be cut, each containing the two junctions that would allow the movement of electrons through them to be precisely controlled. These tiny and reliable devices could be used in all sorts of electrical equipment.
You cannot have the electronic equipment that we have without tiny components. And you get a weird effect, actually. The smaller they get, the more reliable they get. It's a win-win situation.
The Bell Labs team were awarded the Nobel Prize for their world-changing invention, while the European team were forgotten. William Shockley left Bell Labs and in 1955 set up his own semiconductor laboratory in rural California, recruiting the country's best physics graduates. But the celebratory mood didn't last long, because Shockley was almost impossible to work for.
People left his company because they just disliked the way he treated them. So the fact that Shockley was actually such a git is why you have Silicon Valley. It starts that whole process of spin-off and growth and new companies, and it all starts off with Shockley being such a shocking human being.
The new companies were in competition with each other to come up with the latest semiconductor devices. They made transistors so small that huge numbers of them could be incorporated into an electrical circuit printed on a single slice of semiconductor crystal. These tiny and reliable chips could be used in all sorts of electrical equipment, most famously in computers. A new age had dawned. Today, microchips are everywhere. They've transformed almost every aspect of modern life, from communication to transport and entertainment. But perhaps just as importantly, our computers have become so powerful, they're helping us to understand the universe in all its complexity. A single microchip like this one today can contain around 4 billion transistors. It's incredible how far technology has come in 60 years. It's easy to think that with the great leaps we've made in understanding and exploiting electricity, there's little left to learn about it. But we'd be wrong. For instance, making the circuits smaller and smaller meant that a particular feature of electricity that had been known about for over a century was becoming more and more problematic: resistance. A computer chip has to be continuously cooled. If you take away the fan, this is what happens. Wow, that's shooting up. 100, 120, 130 degrees. 200 degrees, and it cut out. That just took a few seconds and the chip is well and truly cooked. You see, as the electrons flow through the chip, they're not just traveling around unimpeded, they're bumping into the atoms of silicon, And the energy being lost by these electrons is producing heat. Now, sometimes this was useful. Inventors made electric heaters and ovens. And whenever they got something to glow white hot, well, that's a light bulb. But resistance in electronic apparatus and in power lines is the major waste of energy and a huge problem. It's thought that resistance wastes up to 20% of all the electricity we generate. It's one of the greatest problems of modern times. And the search is on for a way to solve the problem of resistance. What we think of as temperature is really a measure of how much the atoms in a material are vibrating. And if the atoms are vibrating, then electrons flowing through are more likely to bump into them. So in general, the hotter the material, the higher its electrical resistance. And the cooler it is, the lower the resistance. But what happens if you cool something right down, close to absolute zero, minus 273 degrees Celsius? Well, at absolute zero, there's no heat at all. And so the atoms aren't moving at all. What happens then to the flow of electricity, the flow of electrons? Using a special device called a cryostat that can keep things close to absolute zero, we can find out. Inside this cryostat, in this coil, is mercury, the famous liquid metal, and it forms part of an electric circuit. Now, this equipment here measures the resistance in the mercury. But look what happens as I lower the mercury into the coldest part of the cryostat. There it is. The resistance has dropped to absolutely nothing. Mercury, like many substances we now know, have this property. It's called becoming superconducting, which means they have no resistance at all to the flow of electricity. But these materials only work when they're very, very cold. If we could use a superconducting material in our power cables and in our electronic apparatus, we'd avoid losing so much of our precious electrical energy through resistance. The problem, of course, is that superconductors had to be kept at extremely low temperatures. Then, in 1986, a breakthrough was made.
In a small laboratory near Zurich, Switzerland, IBM physicists recently discovered superconductivity in a new class of materials that is being called one of the most important scientific breakthroughs in many decades.
This is a block of the same material made by the researchers in Switzerland. It doesn't look very remarkable, but if you cool it down with liquid nitrogen, something special happens. It becomes a superconductor. And because electricity and magnetism are so tightly linked, that gives it equally extraordinary magnetic properties. This magnet is suspended, levitating above the superconductor. The exciting thing is that although cold, this material is way above absolute zero. These magnetic fields are so strong that not only can they support the weight of this magnet, but they should also support my weight. I'm about to be levitated. Oh, it's a very, very strange sensation. When this material was first discovered in 1986, it created a revolution. Not only had no one considered that it might be superconducting, but it was doing so at a temperature much warmer than anyone had thought possible.
We are tantalizingly close to getting room temperature superconductors. We're not there yet, but one day a new material will be found. And when we put that into our electronics equipment, we could build a cheaper, better, more sustainable world.
Today, materials have been produced that exhibit this phenomenon at the sort of temperatures you get in your freezer. But these new superconductors can't be fully explained by the theoreticians. So without a complete understanding, experimentalists are often guided as much by luck as they are by a proper scientific understanding. Recently, a laboratory in Japan held a party in which they ended up dosing their superconductors with a range of alcoholic beverages. Unexpectedly, they found that red wine improves the performance of the superconductors. Electrical research now has the potential once again to revolutionize our world if room temperature superconductors can be found. Our addiction to electricity's power is only increasing. And when we fully understand how to exploit superconductors, a new electrical world will be upon us. It's going to lead to one of the most exciting periods of human discovery and invention. A brand new set of tools, techniques, and technologies to once again transform the world. Electricity has changed our world. Only a few hundred years ago, it was seen as a mysterious and magical wonder. Then it leapt out of the laboratory with a series of strange and wondrous experiments, eventually being captured and put to use. It revolutionized communication, first through cables and then as waves through electricity's far-reaching fields. It powers and lights the modern world. Today we can hardly imagine life without electricity. It defines our era, and we will be utterly lost without it. And yet it still offers us more. We stand once again at the beginning of a new age of discovery, a new revolution. But above all else, there's one thing that all those who deal in the science of electricity know. Its story is not over yet. To find out more about the story of electricity and to put your power knowledge to the test, try the Open University's interactive energy game. Go to bbc.co.uk/electricity and follow links to the Open University.
A ringside seat for the changing of the seasons in Autumn Watch, back here on BBC HD from 8:30 tomorrow night. And coming up next, we're off to the seaside with Coast.